Okay, so today we're going to talk about, let me hide these media controls. Okay, so we're going to talk about parallel programming. And let's start off with, make sure I'm recording. I think I am. Good. Okay, so this is like a quick review. Remember what you're doing in milestone 4, you've got a bunch of depots, you've got a bunch of pickups, a bunch of drop-offs, you've got to find the fastest delivery route. That involves estimating the travel time between all the locations and finding a good delivery order. Okay, you got to do that in less than 50 seconds for all the cases. So we talked about this in the lecture, but you can get a better answer if instead of just guessing the travel time by like how far apart are things, you actually pre-compute what's the real travel time between essentially every interesting intersection. Interesting intersection means it's a depot, it's a pickup, or it's a drop-off. Those are the only ones you care about, basically, of how long does it take to get between them. So you could pre-compute a matrix that has the delay. This would be the delay from the kth interesting intersection to the first one, and so on. So there are, basically, if I have k intersections involved in being delivered or picked up, etc., then I've got k squared possible delays that might be useful to me. I can put them all in the matrix. Okay, and we already talked about that in lecture. Okay, so how do we compute that travel time matrix? And again, this is a bit of a review if you already went through the lectures, but it's so that you don't get, why am I talking about this? Basically, I want to show you that we're going to teach you how to write parallel programs, but sometimes people get into a trap of they think, therefore what I should do is just get something going and immediately parallelize it. Improving your algorithm is generally a bigger hammer than going parallel. So you want to make a good algorithm first. So let's talk about the algorithms to get this travel time matrix. So one is you use your milestone 3 solution. So if you got all the way to A star, you've got this pretty fast algorithm to, given one starting point and one ending point, find the path between them and find the travel time between them. So you could run that basically k squared times, right? I could go for every starting intersection that's interesting to every destination intersection that's interesting, run my milestone 3 pathfinding algorithm, store the result. Does that make sense? Okay, so this is like a good question for final presentations. So we tend to ask questions to see, do you understand the course material? So sometimes we ask for complexity analysis. So this is good practice. Okay, so I just said I've got k interesting intersections. It's basically add up all the pickups, drop-offs, depots, that's k. And then I've got a graph with more intersections, v of them. That's all the intersections at a city, maybe 200,000, whereas k is more like 300. Okay, so looking at this code, this is using your milestone 3 pathfinding algorithm. What's the overall complexity of filling in this matrix? And if you, okay, so pretend this is like the final presentation and somebody asked you that. Worst thing you can do is just freeze. Just go, because then you're just going like, give me 0, right? Like, I have no idea. I'm gonna stare blankly at you for 30 seconds. Okay, so I know you're all considering that. Should I do it? Not good practice, don't do it. So even if you get a partially correct answer and you explain your thinking, you will get essentially partial credit for it. This is actually a good practice, not just for the final presentation. It's for if you're at a conference, you present a paper, and someone asks a question, you don't have a perfect answer. Much better to give an answer where you're saying, well, I know this, and I know this, I haven't thought about that, than to say, I have no idea. Same thing after, so it's the same in these presentations, same in an interview, right? In an interview, somebody asks you a question, you can't solve it perfectly. Much better to think through it, saying, I know I could do this, I know I could do that. I'm not quite sure what the best way to attack this is. That's way better than just saying, I'm going to stare at you blankly for 10 minutes, and maybe you'll give me the job anyway, right? So, okay, so that's motivation, that you don't just stare blankly at me. Anybody want to take a shot at this? So even if you're like, I'm not 100% sure, take a crack at it. What do you think? Oh, you're thinking, okay. Oh, I was so excited. I was like, that speech inspired you and you're going for it. So. Okay, now you know what? I'm going to sweeten the pot. First, I'm going to give you a chocolate bar to try. I'm going to give you 3 lifelines. So if you get stuck, you can use a lifeline.
Okay, I'll ask a question. What is the intersections that is that from SRC?
Yeah, so this code is sort of like pseudocode almost, right? Well, I mean, it's basically correct, but this is the range-based for. So this just says I've got some intersections, just like the interesting intersections. So it's like a vector of like maybe 300 things, K things. Okay. These are like the intersections that are actually involved in the traveling system, the traveling involved. So you want to go through that whole list, saying, let's take one of them, call it source. Now let's go through that whole vector again. Take one of them, call it desk. And call your milestone for your pathfinding algorithm and store that in pictures. Does that make sense? Yeah. And you'll see later on those code is a little more correct and really defined data types and stuff. So it's a little bit faster pace. Do you want to go for it or not?
Sure.
Okay, what do you think?
Would it be the amount of n represented in the marks?
So I give you the variables here. K for the number of interesting intersections and V for the total intersections in the whole city. You only need these two variables, that's why I gave it to you.
Oh.
Okay? What do you think? I'll let you guys team up if you want. Totally fine. Okay, so you're now a metahuman, like some kind of like superhuman, two of you together. So what's your answer? What do you think? Okay, so k squared. Walk me through how you got k squared. Yeah? Yeah, so I'm with you. So there is a k squared in the answer. Okay? So now all we got left is what is this? Because you're right. This is just these two loops are k squared. So again, in the final presentation or interview, you already get some credit for k squared, right? So what do you think? Now you need to figure out what's this. So you need to think about what was the complexity of A star. And if you don't fully remember, even just thinking out loud of what it might be is helpful. Times V, because you're going to go through every single intersection, right, in the worst case, in the graph. Almost. So this is very close. There's one thing missing. So in A star or Dijkstra's and A star actually have the same asymptotic complexity. A star just is a little more efficient, and then it'll usually be maybe 3 times faster, that kind of thing. It doesn't search as much of the graph on average, but in the worst case it does search the whole graph. So, and 3 is just a constant, right? So, okay, so this is right. K squared times for this pair of loops. We could look at every intersection of the graph. That's V. We won't go in loops. We won't look at things over and over again. Either on visited flag or we have that best time test. So it's just V. But when we get to an intersection, we basically do this operation of stick all of the neighbors in a priority queue, if we haven't seen this intersection before. And then after we've done that, we basically go back to the loop and we take something out of the priority queue. Okay? So this says the priority queue is order 1. Because it says that priority queue doesn't get any slower as I put more stuff in it. Right? Do we have an order 1 priority queue? So you're saying no. So what do you think? What should we add here? Well, this is the tricky part. Because of those flags, I'm only actually going to process a node once. Okay? Now that I'm using Dijkstra or A star because I do them in a nice order. Okay? So I will include V. But when I process a node, essentially the fundamental operation is 2 things. Check have I already been here with a better time. Okay, that's order 1. Check from the destination. That's order 1. Neither of those things is true. Then I basically update the best time to this node. That's order 1. Then I basically say, look at all my neighbors. Okay, there's only a few neighbors, so that's basically order 1 as well. And every one of those neighbors put them in the priority queue. Okay? But how long does it take me to put things in a priority queue? Because order 1, like if you don't add anything else, you're saying it's order 1. Like no matter how big this graph is, how much stuff might be in the priority queue, it's the same speed. So is our priority queue that good? It's not that good. Okay? So what do you think? Do you remember our priority queue? How did we build it? I know you asked STL for it, but how did STL build it? So, what do you think? Do you remember? Any thoughts on how fast the priority queue is to put stuff in? And we also, at the top of the loop, have to take something out of the priority queue. But it turns out the time to put in, time to take out is the same. So what do you think? Yeah, it's log, and I didn't use n here, I used v. But yeah, so there's a log v. Okay, so that's the complexity of that. I count this as like sort of a team effort. The break, you guys could all like come and get a chocolate bar because almost everybody participated in that. And again, if you get asked this kind of question in the final presentation, think out loud, because if you get it partially right and you express yourself reasonably well, you'll do actually okay. It won't be perfect. Much better than just saying, I didn't actually pay any attention to that part of the course. I have no idea what the words coming out of your mouth are, right? Because, that's not going to go well. Okay, so k squared v log v. Okay, so this is not terrible, but this k squared does start to hurt. So we give you some cases where k is more than 300, fairly big. And so computing this matrix could take a fair amount of time. I'm going to show you how much time later. You only have 50 seconds, so it's doable, but it's going to hurt, okay? Well, actually, with this algorithm, it's not doable. I'll show you some numbers later, but with that algorithm, you actually cannot do this in 50 seconds for the biggest problem. It's just too big. Okay, so how can we speed this up? So we talked about this in lecture. We said, really the A-star algorithm or a single source, single destination Dijkstra's algorithm is not the best choice for this. We can tweak Dijkstra's a little bit to find from one source what is the delay to every single destination. Okay, and now by doing that, we got rid of one of our loops. So, okay, so now what is the complexity of this? This is actually easier to analyze. So the first part is, what's the complexity as a function of k? What's the k part of this? What do you think? Yeah, actually, you gave me the whole thing. Exactly right. So it's kv log v. Okay, and the way, well, once you, I think you know why, but why don't you break it down for me? So again, practice for the final presentation. Why is that the complexity? That's exactly right. That question would get you like a 6 out of 6, right? Or that answer, sorry. The question doesn't get you that, the answer gets you that. So yeah, exactly right. So we got rid of one of the loops. We changed from A-star to this multi-destination Dijkstra, but the multi-destination Dijkstra is not that much slower. It's slower by like a small constant. It actually still looks through the whole graph, as you said. And now it's more likely to look through the whole graph. Instead of looking through a third of it, it's going to look through pretty much the whole thing. That's just a constant. And you still use a priority queue, it's v log v. Okay, so this is actually, that looks good, right? We brought the complexity down. And I'm going to show you some numbers later in the presentation about, what was the impact of this. And again, the purpose of that is to show you don't just think about parallelism and not algorithm. Algorithm matters a lot. Okay, but if you want to go faster than that, I don't know of any algorithm, well, actually, I do know of algorithms a little bit faster than this by a constant factor, but you're not going to use it in this course, okay? And actually, for this case, I guess I don't really know an algorithm faster. This is about as good as you can do, so that's it. So if we want more speed, we're going to use parallel programming. Okay, so let's motivate that. So this, why do we want to do parallel programming? And I guess I'm a semiconductor person, so I think about these things from kind of a Moore's law perspective. So this purple curve is, over the course of 45 years, on a log scale, how many transistors can we put on a chip? And this data goes up to 2015, but it hasn't, if I extend these curves up to 2024, the curves extend basically the same way as you see here. Okay, so transistors have gone up exponentially. That's Moore's law. So we've got way more transistors. In terms of the speed at which we could clock a processor, okay, it actually also went up exponentially for a long time. So this green curve is massively increasing, and then it went basically flat, and it's still flat. If I extend this out to 2024, it really hasn't moved very much. Maybe got a very slight upslope that is almost not noticeable on a log scale like this. Why did that happen? Basically, because of this curve. This is power. For a long time, as we made transistors, we put more transistors on a chip and we made them run faster. We did things like reduce the voltage and the capacitance got smaller, but even despite all that, the power kept going up. And for a long time, nobody cared. But then we hit about 100 watts. And 100 watts, or a little more, you can maybe do 300 watts, is about the limit of what you can get out of a chip with air cooling. Okay, so first it starts getting expensive. In data centers like Google and Microsoft data centers, they spend about 1/3 of the total budget of the data center on power. So power matters a lot. That's including building the data center buildings, that's including buying all the computers, that's including people running it. 1/3 of their budget just goes straight to power. Okay, so that's one problem, it's expensive. Second one is you just can't cool it anymore, right? Like the chip will just melt. So, which is maybe a more fundamental limit still. So we can't actually increase power much anymore, and that means you have to make trade-offs in your transistor design and the design of the architecture of the chip that basically result in you not getting, higher clock frequencies. Okay, that's a kind of a direct consequence. Okay, this yellow line is probably the one you most care about if you're buying a computer. It's basically how much faster can your processor run a program. Now, what's called a single-threaded program, which is basically all the programs you've written so far at U of T. They're all single-threaded. You never even heard probably that term because it's just like implicit. The program just runs through one thread of execution. It starts in main and it does whatever you tell it to do. Okay, so for a long time, processors got faster at running programs like that. Part of it was just that they clocked faster, but this curve actually is going up even faster than clock rate. So the other thing that was happening is they are finishing more instructions per clock tick. So they're trying to do more. And there's actually a lot of complexity in the processor to try to do that. But that also started getting super hard to improve. They still improve it a little, but because clock speeds aren't going up much anymore, and we can only make limited improvements in how many instructions we can kind of work on at once and finish every cycle, single thread performance is kind of plateaued. I mean, it's still going up a little bit, but on an exponential curve, it doesn't look like a very dramatic change anymore. Okay, what does that mean? You've got all these semiconductor manufacturers that can make way more transistors. They want to sell them to you, but they cannot make a much faster core. What could they make? They can make you more cores. So that's what they've done. They basically, you buy a laptop, you get maybe 4 to 8 cores. You buy a server, you get maybe 32 to 128 cores. Because that is what they can build you and have value. Okay, does that make sense? Okay, so multi-core processor, I showed this in lecture yesterday, but basically a multi-core processor is multiple CPUs. A core is really like a CPU. And they all share the main memory of the computer. And nowadays it's common for you to have several of these cores on one chip. So it's hard to buy like a PC processor that isn't multi-core. So until now, you've basically been running programs where your program is just running on one core, and it gets a part of the shared memory. Memory is physically shared, but basically that's the operating system's problem, right? It gives you some of the shared memory, it gives other programs part of the shared memory, and if you ever try to access memory that another program owns, the operating system kills you, and that's a SIG fault. So you didn't really have to worry about this shared memory. That was just the operating system's problem. And you got some value out of these cores, right? You could have 7, our undergrad labs have 8 cores in each computer, so 7 other people could be running on a computer and you generally wouldn't notice much difference. So there is value to that. But let's say you don't have 7 friends who want to share the computer with you, and you still want to get value out of these cores. You just want to make one program run faster. What you need to do then, so basically if you're writing I guess I already said that, but when the programs you've been running to now, you never had to worry about shared memory. It was physically shared, but the operating system handled that for you. It was like all your memory. Now that you're trying to run one program faster, you have, in this example, I have 2 cores. They're both part of my one program. The operating system is perfectly happy to let both of them access all the memory of the program. And it's now my job to make sure that I access that shared memory in a way that's logical, okay? So you need to worry about this shared memory. That's actually the hard part of parallel programming, what's going on. Basically the fundamental thing that makes this hard is you now have, your program has 2 threads or 4 threads or 8 threads running, and they could both modify the same variable, and it's not clear what happens in that case. Right? Who modified it last? Did you think about that? Did you think that in all cases this was okay? That's where most parallel bugs come from. is you're not thinking about there are multiple people doing, multiple threads running at the same time, and they might be modifying the same memory. Okay, so everybody with me on the basics of the hardware? Okay, so let's talk about how we do this. So in a single threaded program, you studied this in 244 basically, or maybe 243. One of those two should have covered this. Does this look familiar? Okay, people are nodding, that's good, because otherwise we've got a pretty big gap in our curriculum. So I'm trying to fill a few gaps in this course, but I'm not gonna fill that one too. So, okay, so you've got a CPU core running, and it's got a program counter that tells it, what's the next instruction I'm gonna execute. The instructions are stored in main memory. You've got a stack pointer, which is telling it where are my local variables. That's also pointing at main memory. And then you actually have global variables that are in main memory. And you have what are called heap variables. Heap variables are the things you created with new. And as long as you have a pointer to them, you can go use them. And you might not directly have a pointer, it might be inside a class. So for example, vector has a pointer inside of it. You don't see it, but it's there, okay? So, okay, so that is what hopefully you're used to. When I go to a multi-threaded program, I now have this second core that's gonna help me out. And it's running another thread, okay? It's not a full program because it's actually using the same memory, but it does have its own program counter. It does have its own stack pointer. So it's executing from the same list of instructions, the same program, but it's generally executing a different instruction, right? There's no reason it has to point at the same one. They're not running in lockstep. Each of these threads has its own stack, so they have their own local variables, and they work just like you're used to. But they have the same global variables, and they also have the same heap variables. So either thread can access the heap variables as long as they have a pointer to it. So you've got a pointer to it, you can access it. It's a global variable, you can access it. Your local variables are yours alone, right? No other thread can get at them. Does that make sense? Okay, so I think I said all that. Let's see, so I think I said all of this already. Okay, what does this mean? So the good thing is we can have these threads communicate just by reading and running from memory, and that's fast. So we get this fast communication through basically global variables and any variables where they're shared. We basically have a pointer, both have a pointer to them. The bad is we have to be careful with this. We have to be really careful that two threads don't conflict in their reads and writes to the same memory. So let's say I have a global variable and two threads write to it. You don't know which one wrote last. So when you write your program, you have to think about that. If that's possible, you have to stop it. Well, you have to stop that from happening, or you have to be sure it's okay, no matter what order those two writes happen. Usually it's not okay. So usually you just try to stop it. Or you try to enforce some order. But generally, if you just say, well, I've got multiple threads, they're all writing the same variable, who knows what the final answer is? Usually that means your program's not correct. You have to think about it harder than that. The last thing I'll say is that in the previous slides I showed kind of one thread running on a core. You can have more threads than cores. It doesn't help you in terms of running faster. Sometimes it helps you in terms of just thinking about how to divide up the work of your program. The operating system will time share the CPUs in that case. So threads will what's called go to sleep. So the operating system says, this one is not running anymore, and we're gonna bring in a new thread. We're gonna set the program counter to point at its instructions and stack pointer to point at its stack pointer, and it's gonna run for a while. So that's another part of the operating system's job, is even if there are lots and lots of threads and lots of programs with threads in them, it time shares whatever CPUs are available between them. So it means you don't crash if you ask for more threads than there are CPUs, but it's also not going to make you faster. So usually you don't try to do that. Let me pause there. Any questions on that, or it's all pretty clear? Yeah.
So, a couple weeks ago, I asked my TA about multithreading, and I heard someone else didn't ask like how it helps. And he was saying that like it's good for like low math, but like you can't do it with like running the rest of your program because it makes everything great, or like it makes it look very complicated. So I was wondering like why that is the case, like why it's good for like low math, but like
Yeah, so I'm going to show you an example next slide of actually how you can make load map use threads, just as an example of how to do it, like really fast in like 4 lines. I'm showing it to you. So maybe I'll answer the load map one, and then I'll answer why other things are complicated. Does that make sense? So, okay, so how do we multi-thread? So basically, when you start a program, you get one thread. So C++ and C define that when a program starts, they create one thread and it starts running main. That's just part of the language standard. That's why you always have to write a main. Otherwise, we don't know, the C runtime doesn't know, well, what should I do? If you want more than that one thread, you have to create them with API calls, or some library that will make the API calls for you. So I'm going to show you 2 ways to do that, okay? This first one at the top is the one that we're going to talk about for the rest of this tutorial, and it's what we recommend if you want to do parallelism, you use for milestone 4. Okay, so that's called OpenMP, or Open Multiprocessing. This uses compiler directives. Compiler directives, this is an example of a compiler directive. Okay, it starts with hashtag pragma, which says this is not code, this is an instruction to the compiler. It's extra information. Compilers are actually, if they don't understand the pragma, they can ignore it, and the program will actually still run correctly. You're giving like hints to the compiler of how could you run my program faster. Pretty much every compiler for C and C++ understands these OpenMP pragmas though, so these are pretty standard. So this says pragma, then it says OMP, which means OpenMP, so that's the kind of pragma this is. And then it says the very specific pragma is I'm a parallel 4. Okay, so what does this mean? The compiler understands that when it sees this pragma, there should be a for loop right after it. And that for loop, you are telling it, it's okay to take the for loop, which in this case runs over 100 iterations, and divide that work up across multiple threads. So instead of saying one core does all 100 iterations, you were saying it is okay to, I'm going to show you an example on the next slide, take 4 cores and give each of them 1/4 of the iterations. And the compiler will actually create 3 more threads for you and have them run just do some of the work, and then it'll destroy those 3 threads when they're done. And your program will keep running with 1 thread again after the for loop. So the compiler did a fair amount of work for you, because to make this for loop run in parallel with multiple threads, I put in 1 line of code. So it's pretty succinct. Does that make sense? Now, the compiler is not magic. It is trusting you that it is safe to do this. So we're going to go through some examples of where it's actually not safe to do this, because it's a compiler. It's kind of like any other program. You can write a program that doesn't actually do what it's supposed to do. The compiler doesn't fix that. The compiler trusts you when you say it's okay to split this for loop up. If you didn't really know what you're doing and it's not okay, it's just going to split it up anyway and your program's not going to run properly. Okay, so that is the easier way to get parallelism. And again, this is a better way to do it for milestone 4. With less code, you will be able to speed up that matrix calculation that I showed you at the start. What is OpenMP doing? Behind the scenes, it's creating threads, giving them work, waiting for them to all complete, destroying the extra threads, and then going on. How is it doing that? Under the hood, it's actually calling the C++ threading library, threading API. That was added to C++ in 2011, so sometimes it's called C++ 11 threads. It gives you more control, but it's lower level code. Sometimes that extra control is helpful. Sometimes it's just kind of in the way. You're writing more code to do the same stuff. Okay, so if you wanted to write this, what do? First, you include the standard library threading header. And here's how you actually, okay, I did it in main, so main would not, you should probably do this inside load map. Maybe after this tutorial, I'll change this to load map. But basically, I'm showing here actually how you could make load map parallel. So what I'm declaring an object of type thread. I'm giving it the name worker thread. And the constructor for a thread in C++ takes the name of a function. So I'm telling it, I want you to make me a thread, and I want it to start running load map streets. And load map streets, let's say it loads remember the databases we give you are divided into 2 parts. There's the streets database and there's the OSM database. So let's say I wrote this function to just load the streets database and process everything I need from there, right? Any data I need to calculate, like street segment lengths, etc., I do it all there. So this line basically creates a thread, and that thread just goes off and does work, and the main thread just keeps on going. So now my main thread goes on to another function that I called load map OSM, and that loads the OSM database and does anything I need to, right? Like maybe loads up some hash tables of how do I map from an OSM ID to an OSM entity pointer and that kind of stuff. So what I've done now is I've got two threads working. My original main thread, and I created this new worker thread that's helping. And we wrote those two databases to be independent, so this is safe, okay? You can do this, you put this in your code, actually it'll work. I'm not saying you should necessarily do that at this point in the course, but if you really want to do it, you can do it. Now, before I go to the rest of the program, like my main thread is gonna finish this load map OSM, and it would just keep running. And here there's a danger. What if it finishes the OSM processing before the other thread has finished all the streets processing? And it goes on to the rest of the program, and the rest of the program expects that both those databases are alive. This would be unsafe. That would be considered a race condition. So I don't want that. So what I do is I use another method that threads have. So remember, worker thread is a thread. It's an object of type thread. That has a join method. What this means is the main thread hits this line, and it calls this method, which will just sit there until the worker thread is also done, okay? So this is the main thread making sure it waits until the worker thread is done, then it'll go on. The worker thread will disappear, it'll be deconstructed, and we can go on to the rest of the program knowing all our data has been loaded. Does that make sense? So sometimes this is the right way to do things, right? For example, to multi-thread load map, this is probably the easiest way to do it, because there's a ton of code here that is going to be executed by this function, and there is a ton of code that's going to be executed by that function. So this is a pretty easy way to do it. Create a new thread, give it that work, wait for it to be done, keep going. Does that make sense? Okay, but now I'm not going to talk anymore about these C++11 threads. We're going to work at this higher level, because for the kinds of things we're going to parallelize, this is going to result in more succinct code from us going forward. Okay, so now let me go back to your question. So your question was load map. So hopefully that explained to you, like, how could I make load map parallel? You can divide it into two big chunks reasonably easily. You can even divide it into more chunks. Like if you went and looked at, well, what am I doing with the OSM data once it's in? I'm loading like 6 different data structures. Well, those probably are also parallel. You'd have to check and make sure there's, data structure 2 never uses data structure 1. But if it doesn't, then you could say, well, load those both in separate threads. Does that make sense? But the biggest bang is actually just using 2 threads. You just get the street stuff going and the OSM stuff going at the same time. It cuts your time a fair amount. Why is that hard to do in your whole program? So some students, for example, ask, could I make my rendering use multiple threads? Like I'm going to loop through all my streets, and could I just say, draw all the streets in parallel? The problem with that is the graphics library you're using is not thread safe. Okay, it has some shared variables inside of it. So EasyGL has some shared variables, like you set one line color, right? You don't set a line color for every single thread. And the underlying libraries that we're calling actually also have code like that. So it's not just like we need to go and change some stuff to have like a per thread data structure. I'm not going to do this, right? Like, I'd have to go in and rewrite parts of Cairo, rewrite parts of X11, various other libraries. So it's not going to work. Does that make sense? There are graphics libraries that are parallel. So like OpenGL, for example, which is being replaced by something called Vulkan. They do allow multiple threads, and because they're targeted at very high performance. They are also much harder to program. Like if you actually go, what does it take to program a modern version of OpenGL or Vulkan? It is wicked, okay? Because you're kind of writing, at this point, little programs that run in parallel on the GPU, as well as multi-threaded code on the CPU. So it'd be very high performance, but it would take you a long time to do. Does that make sense? Yeah, so I guess a long way of saying that is you got to make sure if you parallelize something that all the functions you're calling are thread safe. Now, I guess I'm telling you that we made the streets database one and the OSM database one independent. So as long as your functions are also independent, it's fine. And the natural way to write your functions is kind of independent. But that's definitely not true of the low-level graphics rendering functions you're using, which means it's just going to be a disaster. Okay?
I just have another question. Let's say we use like a mean viewer and like multiple people are using like the same computer at once.
Yeah.
Different cores. Then like say if there are 8 cores using the same computer, will we still be able to do multithreading?
Yes, you can, because the OS time slices them. So you won't crash or anything. You won't get as much performance benefit as you hope to, because fundamentally you got a bunch of people trying to share it. You'll probably get more than your fair share of CPU, right? Like they're now, maybe you create a bunch of threads, so everybody else got one thread, you got a bunch. Maybe you're getting like half the CPU then, but fundamentally you're still sharing. Does that make sense?
Yeah.
When we run your program, we always run it on an unloaded machine, so when we run it, you're gonna get the maximum performance. Yeah.
So, for the worker thread thing,
Yeah.
you give it the function load map streets, right?
Yeah.
Is that just, what would happen if it like had a return type other than void?
It's a bit of a pain. So that's where like this low-level threading library is kind of a pain. So the fundamental API doesn't return anything, and you don't pass any arguments into it. So you have to like set up, well, if I have input data, like where is it? Set it up in some spot and put a pointer in a global spot or something, like get the argument to this, which is a bit of a pain. And if you return something, you have to also set up like a variable that it's going to write into, and you'll check it after. Does that make sense?
Yes.
So you're right. It's a little bit of a pain if you just give it a function name and the function has to return void. And I believe also I have to check the exact syntax of what can you do, whether it can take arguments or not. So does that make sense? Okay, so now we're going to focus on OpenMP though, because it's enough to try to learn one threading style. So I showed you this little loop on the previous slide. Let's look at how OpenMP would parallelize it. So all we need to make it parallel is we put this one line above it. What does that do? Okay, so when execution hits here, we had our main thread. So let's say that's thread 1, that already exists. But OpenMP, let's say we're on a 4-core processor. OpenMP will make us 3 more threads, right? Thread 1, thread 2, thread 3, thread 4. And it's going to divide the work up across them. So it's going to give 25 iterations of this loop to each one of those. And we don't want to go on to the next line of the program until they're all done. So it basically, remember I showed you that join statement? It also makes essentially a join statement. Like the main thread will not go on to the next line until all of these other ones are done. Okay? So I hit this line, 3 more threads get created. The work gets distributed across all 4 threads. The processor will wait until all the threads are done. 3 of them now are destroyed. The main thread keeps going. So as long as this loop was truly parallel, meaning that dividing up the work this way gets the same answer as we would have gotten if we did it all in order on one processor, you can't tell the difference, right? Because only the for loop executed in parallel, the rest of the program is going to proceed the same way as it used to. Does that make sense? Okay. Seems like you guys are with me. Okay, let me do a quick demo of this. Okay, so this is basically the program I just showed you. So I've included OpenMP. So to use this OpenMP pragmas, I just include openmp.h. You also need some libraries. We've already put them in your makefile, so this is all you need to do. And let's change this. Okay, so I've got a vector length. So I don't want to use hard-coded numbers, so we're going to say vector length is 1,000. And I'm basically creating 3 vectors, A, B, and C, each with 1,000 elements. I initialize A and B to some somewhat random data. And then I'm using timers, right? So we've got chrono call here to get the start time, another chrono call to get the end time, so I can print out the time. But the interesting part is this. I've got a for loop here that is basically going through all the vector entries, so from 0 to almost 1,000. And it basically, this I'm just going to print out how many threads are running. So that's not doing anything useful, but I can actually ask OpenMP how many threads are there, because I want to print that out. And what am I doing in the loop? I'm basically computing for every index I, I'm computing what C should be. What is it? Well, it's a function. C of 50 is only a function of A of 50 and B of 50. Okay, so if you look at this code carefully, can you guys read this? Is this big enough? It's good? Okay. Yeah, C of I only depends on AI and BI. The computation doesn't matter. What I did here is a bunch of random stuff, right? Some divides and some percents like modulus. I actually chose those because they tend to be slow, right? The processor, it takes longer to do divides. I basically want to give the processor some work to do. In order to make it worthwhile to parallelize, I want to have some work in this loop. And I didn't want to write real work, so I just wrote garbage stuff using divides. So don't think about that too much. But it is important, the fact that I'm only depending on A of I and B of I. I'm not, basically, it would be bad if C of 50 depended on A of 2 and B of 16. Because if I try to split that up across multiple processors, this isn't really going to work, right? Or it could get problems, right? Actually, that one would still actually be okay. But I have to be really careful that like C of 50 doesn't depend on C of 49. I guess that's actually the one that's more dangerous. If C of 50 depended on C of 49, then splitting up these loop iterations, I can have a problem, right? Where C of 49 is being updated in one thread, it hasn't been updated yet before C of 50 is being computed in another thread. So I have to watch for that kind of what's called a loop carry dependency. But I don't have anything in here. It's nice, basically all my C's just depend on my A's and B's, and I don't change my A's and B's here. So I can kind of look at it pretty quickly and convince myself, if I chop this up across multiple cores, it's going to be okay. Does that make sense? Yeah, so I gave you a bad example. So the better example is I basically am not using a C of a different I, like updating C and then also being limits. If I did that, I have to look at this really carefully. Okay, so let me build this. Okay, so I built it. I'm going to time this, or this program's timing itself, so I want it to be in release build, and it is by default, so I can see optimization is on. And let me look at it again to see which version I'm doing. Okay, so right now, I have this parallel 4 pragma, but it's commented out. So it's going to be the serial version. All right? So let's see how long it takes. And then I don't even have to type time because it's got a timer inside of it. Okay, first thing you see is it prints out the number of threads is 1. Okay, it makes sense. I turned off the parallel 4. And the elapsed time is pretty fast, 33 microseconds. So let's do it again, because with fast run times, maybe it's not that reproducible, but it came out 33 microseconds again. So it looks like 33 microseconds. Okay, let's check a little bit about the CPU. So if I type ls CPU on any Linux machine, it'll tell me all sorts of stuff about my CPU. Okay, so this tells me it's x86, and it tells me I have 16 CPUs. I told you these are 8-core CPUs, so what does it mean? It really is 8 cores. So cores per socket is how many real CPUs do you have inside this chip. Socket is a chip. And then it says each core can actually run 2 threads. So most high-end processors, they have lots of execution units. So a whole bunch of multipliers, usually just one divider, but a whole bunch of adders, a whole bunch of multipliers, a whole bunch of units to talk to memory. Turns out that like one thread often doesn't use them all. You just can't find enough instructions to be working on at once that are kind of safe to do at once to keep all those execution units busy. So most high-end processors actually can run 2 threads at a time. They don't run as fast. They're kind of competing for the same execution units, but that's why it says 2 threads per core. So but that's not as useful as the multiple cores. So really, this is an 8-core processor, and 8 is the number that, if I was paying for this, I want to know what's that number. Don't tell me about 16. The 16 is a little more marketing. Eight is the number I really care about. Okay, so, whoops. Okay, so let me run this again. So I've got 8 cores. I'm gonna go turn on parallelism. So I just have to uncomment this line. My parallel 4 is live now. Build it again. Gonna run it again. Okay, how fast do I think it'll run? So it took 33 microseconds. I got 8 cores. How fast is it gonna run now that I turn on parallelism? What do you think? Divide by 8. So 4 microseconds? Yeah. Okay. I wasn't trying to bamboozle you. That is approximately 33 divided by 8. I rounded off. So, okay, so how many people think around 8? Okay, so around 8, let's run it, see what happened. Okay, so we got 16 threads, so we can tell parallelism is on. It took 730 microseconds. Okay, so you said 4, but it took 730. So what happened? This is a real result, and you were right. Your intuition was correct. We did do the divide by 8 correctly. Yeah, what happened? Yeah, creating a thread takes some effort. You know, let's basically switch to a different function. Let's basically make you a new stack, etc. That actually takes a while. You know, it doesn't take 10 seconds, but it takes more than a few microseconds. So basically the overhead of creating those additional threads was actually more time than the actual work we had to do. So this is the first gotcha in parallelism. Don't try to parallelize really small pieces of work, because you will spend time writing code that will slow your program down. So this was a fail, but let's see if we can get a more positive outcome. So I can easily adjust the amount of work here. So that was a 1,000 element vector. Let's go to 10 million. Okay, so now my vectors are 10 million times longer. I've still got parallelism on. Let's run this. Whoops. Okay, so that took 8.5 milliseconds. So remember that number, because I'm going to go back in, I'm going to turn parallelism off. Okay, and that is like 661. Okay, so I got 8.5 milliseconds versus 61 milliseconds. So, you know, 8.5 times 8 would be something like 68 milliseconds. So this is almost 8x faster, right? It's not quite 8x, but it's close. So, so let me go back to my slides here where I calculated a few more of these numbers. Yeah, so here are a few numbers that I calculated offline. So you go from 1,000, I guess let me explain the bottom number here. So often for parallel algorithms, we compute what's called the speed up. The speed up is how long did it take to run serial, like with one core or one thread, and then how long did it take to run parallel. Okay, so we would like a big speed up number, that the parallel is a lot less than the serial. So when we did 1,000, we got to slow down. Okay, so here I calculated that it was a slowdown of, we got like a speed up of 0.25, meaning it's actually 4 times slower. As we went to 100,000, it still was slower. 10 million, it's actually noticeably faster, 7.6 times. And at 1 billion, which I didn't run, but the billion is also 7.6 times. So once we're up at 10 million, we basically have enough work that the cost of creating the threads is no longer very significant. We don't quite get to 8x the speed up, because there are some non-ideal effects, right? Cores can compete for memory and all sorts of things, but we're pretty close, so this is pretty good. Does this make sense? So don't parallelize small amounts of work. The overhead will kill you. Okay, let's see if we now let's apply our skills to convert this program to be parallel. Okay, so here's a program. I create 2 vectors, A and B. Each has 100 entries. I set all the A's to 50, all the B's to 2. And then I go through and I just basically add the A's and B's and store that back in A again. And then I print them all out. So, I mean, these vectors are too small for it to make much sense for me to parallelize. Like, I'm not gonna get performance on this, but we're just gonna play with, we're gonna use it to experiment with correctness, okay? Because you should immediately go, wait, 100 element vectors, don't do this. But let's say I want to parallelize it. I want to parallelize both these loops. How do I do that? And it's not hard. You go, wait a sec, that doesn't sound like a lot of code. It's not a lot of code. What do I need to do to make these two loops parallel? So this first loop, what do I need to add to my code to run that in parallel? So what do you think? You guys only know a few parallel constructs. Yeah. Yeah, that's all there is to it. So you put that pragma line, if I want to make this parallel, put the pragma line above it again. So it's that easy, right? So I put in these pragma parallel 4s. Okay, so all in OpenMP, all the variables that are created before the parallel 4 are shared. Okay, so all your global variables and all the variables that basically existed before we start the parallel 4 are basically shared variables. Okay, all the local variables that we create inside the parallel 4, those are on our new stack, right? For our individual threads, they are separate per thread. And this matches what people would think, right? Like, well, it wouldn't make sense for I to be a shared variable. It's just not going to work, right? Every one of these threads that's splitting up this for loop, it needs to have its own local variable. And to get the data into them, well, basically they should all be able to access the variables that existed before I got to the parallel 4. Those are like their inputs. Yeah.
So you know this is A150.
Yeah.
That's depending that you know A size, right?
I'm actually specifying A size here. I'm making A have 100 entries.
Okay,
Like that's a
what if-
constructor.
What if it's more than 100?
Well, it can't be because the way I've written it, this is the actual constructor of A.
Oh,
So A will be created with 100 entries. They'll all be initialized to 50. Yeah, that basically is what that line of code does.
so what if A is actually bigger, but then?
Well, A can't exist before I get to this point, right? Like I'm basically constructing A, so before that line there is no A. If I have another A, I'll either get a compiler error or at least a warning. Does that make sense? If I had another A in the same routine, it's actually going to complain, saying what the heck are you trying to do, trying to make two variables in the same routine. If I had a global variable A, then I'll get a warning saying it actually knows what to do. It'll make a new variable A and will hide the global for this routine, but that's actually a really bad thing to do, and you'll get a warning saying you're shadowing a global variable. Okay? So it's a long way of saying, yeah, there's no A before this. Okay? Okay, so that's what this is going to do. What do you think the program output of this will be? Okay, so I create A, every entry is 50, create B, every entry is 2. I add A and B and I store it back at A. And then I print all that. So what's the program output going to be? It's, yeah. Right, so A of 0 equals 52, or is 52, A of 1 is 52, etc. Does that make sense? And I print out like 100 lines of that. Okay, that makes sense. Let's see. I'm going to take a 5-minute break. I want you to think about what that program's going to output, and we're going to have a contest which might illuminate what it's going to output. Okay? So take a break, and come back, and then have two of you like compete at a typing contest. Okay? Which I promise has some relevance to multithreading. Otherwise, 500 again. Okay? I think we've all answered some questions. Grab a chocolate bar if you want. Okay? So. Okay.
Can I ask you a question, or should I save it to the end?
Sure. How long is it?
It's not relevant to course content at all. So.
Okay. Oh, I should tell you guys how long the break is. How about we take a break till 4:18, okay? Because I'm probably a few minutes behind due to my monkeying around at the start of the course, or start of the lecture. Yeah.
So I heard that, I remember in the seminar course, you talked about making like a video game class or something.
Yeah, I'm thinking about it. I'm going sabbatical next year, so I am actually talking to the computer science prof who does that, and I'm figuring out what I can fit into my schedule.
That's awesome. But I figured I wanted to do something related to video games this summer since I couldn't quite find an internship for myself, and I kind of wanted to do like a side project.
And I heard there are these things called like game engines, kind of, where
Yeah.
you set the whole thing up and you make it in parallel to your game.
Yeah.
And I was just wondering if you had any like tips or tricks or like anything I should start with when it comes to that.
So the two big game engines are Unreal and Unity. This is part of what I'm going to be doing on my. I'm doing many things in my sabbatical. I'm going to be playing with these two. Unity is generally considered by people to be kind of easier to get going on. And if you're going to do a 2D game, Unity is kind of agnostic whether you're doing 2D or 3D or whatever. It's the language you program in is C#, which is not too different from C++. C# is Microsoft's version of Java, basically, which is itself a simpler version of C++. So it's the one that most people gravitate to when they're basically, I want to program something and it's not, I don't want it to be too hard. And it's a good game engine. Lots of like good games are made with it. Unreal is programming language is C++, so you actually know the language. This is one thing that people go, Unreal tend to be harder because if you're kind of a self-taught programmer, C++ is a somewhat more difficult language. Unreal is higher performance. Okay, so like for like AAA games and animators, my brother-in-law teaches computer animation, so animators love Unreal. Okay, if you want like the best graphic quality, Unreal is where it's at. It's fundamentally, I mean, maybe it's possible to do 2D, but it's more set up for 3D. People use it not just for games, but like even some movie studios now use Unreal, but they use it for like architectural walkthroughs and so on. So highest graphics quality, locks you a bit more into 3D because it's set up with sort of a sort of a game framework of like how would you do things, and that game framework is more like you're thinking 3D. So, but either one is very usable and useful to learn. Does that make sense?
Yes.
The high-end game studios probably gravitate a bit more towards Unreal. The hobbyists, it's somewhat changing because Unreal's licensing has gotten really good.
Okay.
But the hobbyists have usually gone more towards Unity. That's probably still true. But Unreal's made its licensing pretty attractive.
Okay.
So you can play with both of them a little bit to sort of make a decision. But that's like kind of without having directly programmed in either. I've done some background research on the scuttlebutt. That's the scuttlebutt.
Do you think it'd be too hard to make my own?
No, people can make their own games. Depends how hard you make it, right?
Like make my own engine.
Oh, make your own engine. That's going to be hard.
Okay.
You probably learn a lot trying to do it, but there's a lot in these engines. And especially if you want it, I mean, your engine's going to be a lot simpler. Like part of what it is, I've looked more at Unreal than Unity for this. One of the things I like about it from the point of view of teaching is ece297 has a lot of interesting profiling tools in it for the CPU and the GPU. Because a big part of like these engines, they provide a lot of value, right? Like they organize your scene, that's one value. They have high performance, very high quality renderers, in particular the Unreal one. Well, both are really good. The Unreal one's even better. So if you're gonna go off and write your own high performance renderer with ray tracing and so on, and this is like gonna run partly on the CPU, partly on the GPU, this is like some pretty hardcore programming.
Okay.
Does that make sense?
Yes.
Now, you don't have to do that. You can say, look, I'm going to make this much simpler, but your performance won't be anything approaching what they do.
Okay.
So it depends what you want to do. If you want to learn about graphics rendering, you can start making, and then they have physics engines too, which do the collision detection and so on, which is also a fair amount of work. But, so you're going to catch up, you're not going to catch up with what they do.
No.
Actually, one of the other nice, interesting things is Unreal is open source. You can grab all the source. And this is actually one of the other things that's been helping them a lot. They're essentially a bit more of a learning curve is what most people say, but their technology is probably the best, and it is extensible. You can actually, if you made a pull request that they thought was good, you could actually modify their engine. And on your own machine, you could modify their engine. Now, obviously, you're starting with a very complicated engine, This is kind of like sort of saying, I just bought a sports car, could I like modify the engine? Sure. The modifications may not be a good idea. Do you know what I mean? So, before writing your own, I definitely suggest you start with those.
Okay.
Because then you also like go, okay, how do I use this? I can even read the code for certainly Unreal. How does an engine work? And maybe you go, this is fun, and maybe I'll extend it. And maybe you decide you want to write your own, but you now also have like what are some of the paradigms they use to organize things? So does that make sense?
So you're saying this summer, instead of making my own, I should familiarize myself with like ones that exist first?
I mean, that'd be my advice, right? Like making your own where you've never used one that exists is a little bit of a dangerous prospect, right?
I agree.
So good luck.
Thank you very much.
Wait.
Okay, get the computer close to you.
Okay.
Ready? There's your text. Ready? Got it? Yeah. Go.
Wait,
Wait, what?
where's my text?
Where is your text?
Oh,
What's going on here?
restart.
Hold on.
Wait.
So I think we have no text. So this is like a false start. I'm a bad Olympic judge. Okay, ready?
Oh.
Okay, go. The accuracy looks moderate.
Oh shoot.
Keep going though. Go fast. You're gonna make it. So.
Yeah.
Did you finish? Okay, so I declare this a tie. You each get a chocolate. Okay, what?
I was actually practicing for this during the break.
Okay, what just happened? So this is relevant to the program we were just talking about. Okay, so this text does not look like they're great typists, right? Individually, probably very strong typists, but they're both typing into a shared program with two keyboards, with no attempt to synchronize between themselves. Okay, so they are like human parallel for loops, right? But this was not a good case to actually run in parallel. They're just both typing as fast as they can. So let me unplug this and move it back over here.
We made this comment so many times. I can't believe we were making fun of this car. Yeah, it's the photos. It was the photos.
So this is chaos, right? This is like parallelism where they're both typing into a shared program with no synchronization. Okay, so let's think about that program that I showed you. Let me switch over to it. And we know what it should output, right? It should output A of 0 is 52, A of 1 is 52, and so on. But let's go actually see what it does output. Okay, so I need to go up one. So let me make this one bigger. Okay, so this is the program that I just showed you, right? Two parallel fors. We know that it should output, A of 0 is 52 and so on. Okay, but if I, actually make sure let me comment this out. Okay, so there's a line here that I haven't explained yet. Let's comment that out because we don't know what it is. Okay, so what does it print? It's pretty chaotic. It's not quite as chaotic as what we just saw, but it's not great, right? So you see it's mixing up, it's basically mixing up the output from different loop iterations. And sometimes it's mixing it up pretty badly, right? Like individual lines don't make any sense. Sometimes we get a line that makes sense, but sometimes we get lines that don't make any sense. What is cout? What kind of variable is cout? Is it a local variable? Is it a global variable? What is it? Do you guys know what cout is? So cout's a global variable, right? Anybody can write to it. All these threads are writing the same global variable. So they're all, and there's no ordering between them, right? When I had just a single threaded program, there wasn't ordering, but now I have 8 different threads and who knows who writes what. So we're getting things coming out, sometimes gibberish, right? Because I was partway through running a line and I got a different line written in the middle of it. And if I run this again, this is another thing that happens, is it'll produce different output. So exactly what it prints every time is a function of how these threads get interleaved. So you see there's some lines here that didn't occur before. When you have this kind of parallel bug, it's called a race condition. One of the things that happens is your program becomes non-deterministic. So it makes it very hard to debug. Because every time you run it, it will produce a different answer, usually incorrect. But you run it again, produces a different incorrect answer. So you have to recognize that it is a parallel bug. Now, the solution to this, one solution is I could just say, let's not run this in parallel, okay? So that'll fix this. But let's say I wanted to keep running this in parallel. Maybe I was doing a bunch of work in this loop, most of which is actually useful to do in different threads, and only this print is kind of my problem. I can put this pragma in. So it says pragma openmp critical. What that means is the next block of code, which in this case is just one line, will be run by only one thread at a time, okay? So it's what's called a critical section or a lock. This is going to prevent 2 threads from both being like printing parts of a line on top of each other. Okay, so let me rebuild this, run it again. Okay, and if you look at the output now, every line makes sense. I don't get any more of those weird lines, and I don't get any more of them because I marked this critical. Basically, that line of code will be run by only one thread at a time, guaranteed. So I never get a line that's interleaved. Now, I don't know what order the threads are going to hit that line in. So I still do get, like it turns out that the very first entry processed is 52, because whatever thread got started at entry 52 happened to be extra fast. And then after a little while, whoever got entry 34 got something done. So my output order is still different. And you can see like A of 1 and stuff, like this thread for some reason was a bit slower. So it came out last. But every line makes sense. But if I actually expected all these lines to come out in a certain order, well, there's nothing that makes that happen once I go parallel. So if I'm not okay with that, I shouldn't have gone parallel. Does that make sense? Yeah. Yeah, I mean, what happens when you put, so first, 100 iterations, not enough, right? That's the first problem. Second problem is the only work in that loop was that print. By making it critical where only one thread can execute at a time, I basically destroyed any possibility of speeding things up. So if you make everything critical, there's really no point in making it parallel. But if you had a whole bunch of work and just a little piece of it needed to be like, make sure only one thread does this, that's where you use critical. Does that make sense? It's the block of code right after it. So a block, like if I wanted more code to be in the critical, I could put braces around it. Because I could make a bigger block if I wanted. This particular block is just one line. But again, I could put like 12 lines of code in a set of braces, and then we'll apply to all 12 of those lines of code. Okay, so let me go back to here. Okay, so yeah, so this critical section, let's see if I can get this going. So I guess one of the things I just showed there is, again, highlighting that OpenMP does not check if it is safe to take this loop and split it across multiple threads. Like what I just did was not safe because I had all these threads writing to a global variable. OpenMP doesn't catch that. It trusts you know what you're doing. In general, it's not really possible for it to catch that, right? Like if it could catch that kind of bug, it could pretty much write the program for you. So no compiler can do that. And then we use this critical keyword, or this critical pragma, to basically serialize access to this one line or block of code. Okay, so the critical is like a traffic cop, right? Like who goes, one person goes, everybody else wait, okay? So you can use that. But if you find you're putting critical all over, you should probably just go, this is really not parallel. I probably just shouldn't be doing this. Go just accept it's serial. Okay, so let's go on to pathfinding. So that's it for kind of simple programs. Let's talk about actual M4. Okay, so I told you that there was a reason I was redescribing some of the algorithms. These are results for one of our big test cases, one of the, what we call extreme test cases. So in this one, the number of, well, there are 175 deliveries. So each has a pickup and a drop off, and there are 20 depots. So that's 370, interesting intersections. K equals 370. We do this on Toronto. If we use the K squared approach, right? We use our milestone 3 A star solution. This takes 1280 seconds to fill in that matrix of travel times. So we can't use it, right? We only have 50 seconds. This is going to be a hard fail. If we take that algorithm and we make it parallel, it speeds up by almost 8x, but it's still not fast enough, right? 168 seconds. If we change the algorithm, right? So we go to multi-target Dijkstra, which is not K squared, it's K. It's a bigger hammer. That gets us all the way down to 39 seconds. So now we could use that. And then if we take that algorithm and we parallelize it, well, we still get almost an 8x speed up. So now the total runtime of this is down to 5 seconds. So now for 50 seconds, this is actually not even going to be a big part of our runtime. We can use most of our runtime to kind of do perturbations and multi-start or whatever we feel like to try to find a good delivery order. So our total speed up here is 250x. And most of that was algorithm, right? Algorithm was the bigger hammer. So think about algorithm before parallelism. Is everybody with me? Okay, sounds good. Okay, how do we parallelize? Now, but let's now say we got the good algorithm, multi-destination Dijkstra, we want to make it parallel. How do we do that? And I'm showing you some kind of a skeleton of code, right? There's obviously lots of code redacted here. We need a wavefront. We need this vector of nodes where we're going to store our best time and our reaching edge, right? Like what's the best path we found to every node. I made both those global. And then I got one more global variable. This is like a vector of my K intersections, right? These are like the intersections I'm actually trying to find paths between. Okay, I'm gonna have a for loop over all of the starting intersections. And how many of you use this kind of range-based for? You understand that syntax? If you don't understand it, it's just a shorthand that C++ supports. It means exactly the same thing as this. In fact, this is what the compiler turns it into. So it's just going through my key intersections vector, and it's basically saying, okay, get entry I, go find the intersection ID that's stored there, let's call that the source, and now let's go call our pathfinding algorithm, which is this multi-destination Dijkstra. And we're calling it with what is the source intersection and what is the vector of all the destination intersections, okay? Don't worry if you go, I don't know if I understand all that code. Doesn't matter. Like I'm kind of just showing you a skeleton that is realistic of how you would write this code. In this find paths, it's basically very similar to what you wrote in milestone 3. The heart of it is going to be this while loop that basically goes through pushing stuff in the wavefront, taking stuff out of the wavefront. Okay, so is everybody with me on this sort of basic code structure? Okay, so I want to make this parallel. So I put OpenMP parallel for in front of my for loop. And now every one of my, I've got K path searches to do. And now I'm basically saying, well, you can have multiple threads doing path searches from different source intersections, right? Overlapping the loop iterations, that's what this means. So let's first think algorithmically. Does that make sense? Does it make sense that you could actually say, if I have 8 cores, that I could actually have 8 path searches going on at once, each one starting at a different source intersection? So what do you think? Okay, so I see people nodding. And yeah, you can. I mean, otherwise this is a very poorly thought out tutorial. If I get here and then I go, oh my God, what have I done? But that's the first thing you think about. Like, does this make any sense at all? Because there are some algorithms where you go, this doesn't make any sense, right? This is not actually, these are all these dependencies, there's no parallelism here. So the algorithm is parallel. I can do this. Okay, so now is there anything in my code that is bad, right? Like, so if I've done everything right, the algorithm is parallel and the code doesn't have any problems, then I'm done, right? This is gonna work. Probably you're not done, because the tutorial's not over. Is there anything in this code that makes you nervous? So this is now where maybe I've got an algorithm that's fundamentally parallel, but I coded it in a way where I've introduced some problems. And I have. The way this is coded, I haven't shown you all the code, but I've already shown you enough for you to know that if you think about it, there's a problem here. What do you think?
Isn't that second block like a while loop?
No, this is actually the correct pathfinding, you know, like a very skeleton of it, right? So the while loop's okay. Or what are you worried about in the while loop? Maybe that.
It's just that I just thought that it would run the same thing on like 4 and 4.
No, so I guess I haven't explained this fully, so it's maybe a good question. But so when I put a parallel for on and there's a function call inside of it, basically the iterations of this for loop will be split up across multiple threads.
Oh, I thought it.
And yeah, so it's right there that's going to be split up across multiple threads. Inside that for loop, it's okay if those threads call as many functions as you want. Each of them are just all off calling those functions independently. It's fine. There's no requirement that all the code has to be in the for loop. And in fact, that would rarely be the case. You'll normally be calling all sorts of functions. Yeah.
Isn't that like when you look through different paths, you have to like put like flags like for like the main like global nodes vector, and like with that running before I mess that up?
Yeah, so this global should make you really nervous. So the algorithm is parallel. Okay, I can do a path search from this starting intersection, at the same time I'm doing another path search from this starting intersection. I'm getting different data. It's all fine. But what I've done is, let's take the wavefront. I made a global wavefront, which means every single one of these find path calls, I can have 8 of them, for example, running at the same time. Each of them starting from a different intersection. They're all using the same wavefront. Like, what does that mean? Like, I'm putting in nodes with what is the time from my source, but everybody's got a different source. But they're all shoving it in the same wavefront. It's madness, right? Like, you can't even figure out what is that. It's just garbage. So that's a problem. This is also a problem, right? I've got this nodes vector, which is storing what is the best time in the reaching edge to get to every node. It's like, how did I get here? But I actually have 8 different path searches going on at the same time from 8 different spots, and they're all updating this vector with just completely incompatible updates. What was the minimum time from this source? What was the minimum time from that source? What was the reaching edge in this path search? It's complete chaos. Okay, it's like every bit as chaotic or more than this typing at the same time. So this is never going to work. It's going to crash in. I'm actually going to demonstrate it later to show you how it crashes. It just crashes in every way you can imagine, right? Like, this will be chaotic. Does that make sense? Okay, so how do we fix it? Not going to work. How do we fix it? Well, yeah. Yeah, so everybody needs their own copy, right? Like, this path search cannot work with these globals. It's actually another reason why global variables, like excessive use of global variables, is considered bad practice, right? Here's a case where the algorithm is fundamentally parallel, but if I coded it with global variables, I actually can't parallelize it because I made everybody talk to the same variable. If I made these local variables, okay, which is what I did here. So I just took these. Whoops, not all of them. Okay, so I took these, and I basically said, well, there's no real reason they have to be globals. I'm not really actually setting them up before the algorithm, so I can just push them down to be local variables inside find paths. And every variable that's created after the thread starts is a local variable, right? So these are, well, this is private to that thread. So these new variables that I've created inside find paths, every thread is calling find paths on its own. Every thread gets a different wavefront. Does that make sense? They don't interfere with each other anymore, so this works. And it wasn't that hard, right? I just had to move these variables into local. So this is a general technique for parallelism. It's called privatizing a variable. So you push a variable down to be more local if it wasn't already, so that every thread gets its own copy of it. And that's the natural way to make sure this algorithm is going to work. Does that make sense? Okay, how about this one? Okay, so this variable is still a global. So we got rid of our wavefront, or our wavefront nodes, vectors. We didn't get rid of them, but we pushed them down to be local variables, and now that's good. Every thread's got its own copy. This one's still, let's say, a global variable. So it's still created outside of where before my threads are created, and every thread's going to get the same one. Is that going to be okay? So, what do you think? Seems like you have an idea. Sorry, I have trouble hearing you. Oh, okay. So you're saying this one's okay because we don't change it. Is that right? Yeah. So this one actually is okay, you're right. The reason is because we're only reading it. It's actually natural for this one, it doesn't have to be a global variable, but it generally is going to be created before our parallel for because this is basically its input. So it could be a global variable, if our coding's a little better, probably is like a local variable, but a local variable created before we get to this line. And it's fine, because we never update it inside our parallel for or any of the routines that it calls. It's okay to have many threads reading from the same variable. They just can't, you can't have many of them writing to the same variable, or you can't have one writing and others reading. Those are race conditions, it's gonna be chaos. Yeah?
Just a quick question about like the nodes. Like originally it was a global vector. So in Amplitude when we made it, the node was like a global vector because like both the H algorithm and the traceback function needed it. But in this case, it would make it part of find paths then.
Yeah, if your find path does, like basically if you have a routine, like find path basically calls find path forward search, and then it calls backtrace, then it's fine. It's a local variable that's created before either of those routines. Does that make sense? So you can, they kind of make like a parent function and create it in there, and then pass it into the sub-functions. Or you can make one big function, but that's not as good practice. Does that make sense?
Yeah.
So there's really no reason in milestone 3 that has to be global. For lots of people, they probably didn't write it as global, in which case it's already fine. But if you did, you can push it down into, if you have to, you make a new parent routine. Does that make sense? Okay, so this is pretty common too, that you have lots of variables that you set up and you never modify them. Okay for all the threads to share that. In fact, you have all the state that you created in load map, but all those global variables are set up in load map and you never change them. So they're all okay. You don't have to go mess with that code. It's gonna work. It's again another reason that with your global variables you want to be kind of disciplined. That's made it easier for you. Okay, another question. So I've been talking about globals. Let's say I'm a bit better programmer. I didn't use global variables so much. So these are local variables. Okay, so I made a function called preload time matrix. And basically I now make local variables. I make my priority queue, I make my nodes vector. So not global anymore. Is this okay? Do you like this or not? No, this is still not okay, right? It's not just global variables, it's any variable that was created, outside of the parallel for, like before you got to the parallel for. So outside of the parallel for means, before the parallel for. It's okay for variables to be created in things the parallel for calls. That's kind of considered inside the parallel for. Okay, so yeah, this is not good enough either, right? We need to push them deeper down. Okay, so let me demonstrate that. Okay, and this is like, this is one of those scary demos where debugging parallel code is actually hard. So it's like one of those demos where it's also like you're much stupider when you have a whole bunch of people watching you use an IDE. So there's a non-zero chance of this going south on me. We'll see how this goes. Okay, so let me zoom in a bit. I think I don't want to show that to you. Oops. Oh well, that was possibly part of the value of. Sorry. Oops. I might have to edit that. Okay, so that's one of the interesting things about recording. Like if you're not recording, you're like, there's no way anybody could read that fast enough. So. Okay, so let me go back to, let me close a couple of these things. Okay, get out of M4, go back up here really fast. Okay, that is safe for you guys to read. So let's look for parallel. And let's see, that's not the one I want. Okay, so this is in our better solutions, right? So you see on the leaderboard we have multiple solutions that are written by the teaching team. In our better solutions, the better 2 actually, we use exact travel times. Okay, the weaker 2 we don't. We just use, one of them uses no real optimization, the other one uses geometric distance. But for our better solutions, we need to fill in that matrix. So that's the first thing we do, and I've basically shown you the code for that. We go through all the source intersections and we find all the paths to all the destinations, then we store, okay? And I'm going to, let me turn off this parallel 4. Okay, so we got a parallel 4 to turn this parallel. I'm gonna, let's see, make sure this is release build. So I've copied over one of the unit tests. The particular one that I've copied over is a relatively small one. Like the number of interesting intersections is only 54. So it's like 25 deliveries, 2 depots. So it'll run pretty fast. I always want to test speed with release. So I can either build release or unit test release. And so I'll build this, make sure it's up to date. And while that's running, I'm going to go check that I have my pathfinding working for the first demo. Okay, that looks good. Okay, so now I'm going to run this. And all I want to see is that it actually works. I might have to, okay, good. Okay, so it finished, and let's see what's interesting about this. Okay, let me make sure I've got the right one activated. Okay, that looks fine. Okay, so the time this took is 5 seconds. Okay, so I pre-computed that matrix, but for a relatively small problem, and I did it with no parallelism, but a good algorithm. Took 5 seconds. Okay, so let's go back and I'm gonna go look for that parallel 4 again. Okay, so this is my pathfinding algorithm. I'm just gonna turn on parallelism. Okay, I'm gonna rebuild. So remember 5.2 seconds, run it again. This particular algorithm that I'm running, most of the times in the pathfinding, because I'm running a greedy algorithm. Greedy algorithm is really fast. Once I have all that matrix filled in, there's really not much time left. So I'll run it again. Load map is taking most of the time. We don't count load map as part of your 50 seconds. So you've got 50 seconds. Okay, this went from 5 point something seconds down to 0.7. Okay, so I got again around an 8x speed up. On this small problem, I don't really care, but on the bigger problems where it would have taken me 40 seconds or so without parallelism, this would be helpful. So I did get a nice speed up on this. Now I'm going to show you, okay, so I've basically put a couple of bad things in the code. So I'm going to uncomment this. So this bad parallel global, what this does is without hacking the code in front of you, I have just changed my, that node vector. We called it all nodes, but this is what stores like the best time, the reaching edge for every node. And I just converted it from a local variable to a global variable. Okay, I basically have a local variable version written. I have a global variable version written. By changing this define, the global variable version just became active. Okay, so now I'm going to compile that again and run it. And we'll see what happens. I actually get a warning. That warning is actually telling me you have a global variable and a local variable with the same name. And so actually, if I was really programming this, I'd go look at that warning because the compiler's saying, this code looks kind of ugly, so I should actually go fix that. Not going to fix it because I wanted to break my code. Okay, so I'm going to run this. Okay, so what happened? Okay, it didn't work. I got through load map. And then it says, okay, starting your traveling courier problem. Can everybody see this, or should I make this bigger? You guys read this text or not? Okay. I got double free or corruption abort. Okay, this is what happens when you just have data like races like this. You go, wait a second, how did I have a double free? I didn't write a double free. I have multiple threads that are just banging away on this vector. It's really hard to say what's going to go on, what's going to happen, right? Like if I've got calls to the standard library, we don't know what's going to happen. So it turns out I actually corrupted memory, and it's because of this bad global variable usage in parallel programming. And one of the things you should do if you have a bug that seems like it might be due to parallelism is turn parallelism off. Okay, so I'm going to go back to let's see. I'm going to go back to m4.cpp, and if I suspect parallelism might be an issue, you turn it off, you recompile, and you run again. Okay, so this global variable that I'm using, it's deadly with parallel programming, but it did actually work serially, because I only had one thing trying to work with it. So I'm going to recompile, I'm going to run, and now I expect it to be slower, because I turned parallelism off, but I want to see, does it work? Okay, and it did work. So my advice when you get a bug in a parallel program is the first thing you do, turn off parallelism, see if it goes away. It doesn't mean you haven't solved the bug, but you go, I gotta look at the parallel code. Do I have race conditions? Because parallel code is hard to debug. So first thing I want to know is my serial code works. Also in the agile spirit of you always get things working and improve, it means if you can't figure out the parallel bug, you just submit with the parallel stuff disabled. Like you have a backup strategy, and you always want those backup strategies. Okay, so now let me go back to M3. No, actually, I'm going to go to M4 again. So I now know my current code doesn't work with parallelism, but at least it works serially. Now I'm going to go debug it. So I'm going to switch my configuration to debug. It'll run slower, but I need to I want to run the debugger on it. So the debugger will work with multi-threaded programs. It is a little bit harder to interpret though. So if you kind of go debugging, I got to keep a lot of stuff in my head. Okay, you were debugging with one thread. When I run this, OpenMP is going to run 16 threads, okay? Because the processor says I can run 16 well. OpenMP says, sure, we'll run 16. So I'm only getting 8x speed up, but it's running 16 threads. So I've just built this in debug. I'm now going to run it through the debugger. I'm not setting any breakpoints right now because I actually expect this to crash. I'm just going to let it crash, and I want to go look at the call stack to see where it died. Okay, so I'm just debugging it. It's going to run slower because it's the debug build. Let's make this a little bigger. Okay, so let's see. Oh, I actually have a breakpoint. Okay, so I have a leftover breakpoint from another tutorial. So I'm going to get rid of that breakpoint. I guess maybe this is useful. I actually had a breakpoint in my code, and maybe I'll show you what happens. So you can still set breakpoints, you can still single step, etc. But if I look at my call stack, look over here in the call stack, you'll see it says paused on breakpoint, and it tells me where I am, right? I'm in this function, which is my pathfinding algorithm. I can go back and see, well, where was that called from? This is the kind of main control routine of my pathfinding algorithm. One level further, okay, you should recognize that one. It's got the parallel 4. If I go down though, or let's see, I'm just going to collapse this. You see all these other paused. What are all these other things? These are other threads. Okay, so you've never seen this before, but it's actually showing me 16 different threads, if you count that. So one of them is paused on the breakpoint. The other ones are paused, because what the debugger does, as soon as one thread hits a breakpoint, it stops all of them. Okay? You don't know where the other ones stop. So if I go look at another one, let's see where this one is. This one's actually still getting set up. This is actually in the standard, this is in the low-level C runtime library. This thread still hasn't gotten set up. Okay, so one of them, probably this top thread was my main thread. And it got ahead of the other ones. It's already gotten into the start of the pathfinding algorithm. This one is still getting set up. Let's look at this one. This one actually got into the pathfinding algorithm too. So I can go look at, and I can look at variables. I can look at like, well, you're in the pathfinding algorithm. Which of these interesting intersections, which number are you on? It's on number 12, okay? And if I look at a different thread that's actually gotten started up and is in this routine, it'll be on a different one. So I can look at all their variables, I can look at where they are. Okay, I just cleared the breakpoint, and I'm now gonna say, let's keep going. So I'm gonna say, continue. And I already know this isn't gonna go well, and it didn't. Okay, so down here, it says thread 16. This test libstreetmap, that's the name of the executable, because I'm running the unit tests. Remember those build test libstreetmap? So it says thread 16 received an abort signal, and so it now says I'm switching to it. So what the debugger does is in the call stack, it will kind of highlight or switch to what it thinks is the most interesting thread. So it thinks, well, the one that just died is probably the most interesting. And so it switched to that one. But I can double click on any of these. I can go look at other threads if I want. So let's look at this one. It says it's paused on exception. Okay, so this is my thread that just died. And the debugger is just showing me how it died. This is the abort function. This is like way down in the standard library. I don't care about any of this. Basically, this is saying it was doing some memory allocation when it died. I want to get back to some code that I recognize. So this is this is actually my code. Okay, this is part of my find pass from intersection. And you can see it's trying to resize that vector of nodes. Okay, so it's doing a resize on it. So you want to look at what happened. I crashed. A clue is I was working with this vector. So maybe that vector's got a parallel problem. Turned off parallelism, it all worked. Parallelism on, thread that crashed is looking at it. I can go look at some of these other threads. So let's say I look at this one. So this one, again, there's a bunch of low-level calls. I want to go back to something I recognize. Actually, it's also trying to resize that vector. So at this point, maybe I have a flash of insight of, wait a sec, that's a global variable. I've got two different threads trying to resize it at the same time. I wonder what happens. Because the standard library has no idea what to do with that. That's kind of madness, right? And so on. So I go look at a few more of these threads. Let's go look at this one. Actually, this one's trying to resize it as well. Okay, so this might give me a whole bunch of clues of like, this looks pretty chaotic, and hopefully gives me the ideas to go look at that one. Does that make sense? So now I stop debugging this, it's already crashed. Okay, so just to demonstrate this fully, that was one of these bad global variables, right? That's what happens when I change the node one. Let's just see what happens when I make the wavefront global. Okay, so I'm gonna make this one a local variable again, which is good, but I'm gonna make my wavefront a global variable, which is bad. So let's see, I just changed that, I'm gonna rebuild, and then I'm gonna run the debugger again. Okay, again, get some warnings. The warnings that it was giving me were shadow warnings. That means I've got a local variable and a global variable with the same name. Super bad practice. Okay, so I should go fix it. Might have saved me a lot of pain if I wasn't trying to make pain for myself. Okay, so I started the debugger again. I don't think I have any breakpoints right now, so this will either run to completion or it's going to crash. And let's see. Okay, and it crashed. So let's see what happened here. So you can actually see it create the threads, right? You see a whole bunch of threads get created. And then I'm going to bring up the debugging pane here. And here's my call stack. And you see there's one that's paused on exception. So this one crashed. If I go look at it, again, I want to go back to code I recognize. It's in the priority queue. I was trying to push into the priority queue, put something in the wavefront, and that crashed. Let's go look at where somebody else is. This guy is not in the priority queue. If I look at this one's not in the priority queue. Okay, so I saw the one that crashed is in the priority queue. I might look at a few of these other ones, see if anything else is going in the priority queue. But so far, I haven't seen anybody else. Let's see. Okay, so I have an idea it might be the priority queue. If I look through all 16 of these, I might find somebody else in the priority queue too, because that's a common problem. One last thing is, this is a race condition. I have multiple threads using the wavefront with no synchronization. Okay, so it's chaos. If I just run this again, so let's go back to Makefile Tools. If I run this again, I won't necessarily get the same crash. Okay, that's the challenge of this non-deterministic behavior. So it's very unlikely to work. Well, I know this isn't going to work. It's crazy. There's basically no chance it's going to make it through to the end. But it may not crash the same way each time. Okay, so this has not crashed. But it also isn't done. Okay, this took 1 second, less than 1 second before. Okay, so I don't know why this is taking so long to go through it. So I'm going to wait a few more seconds. This is probably hung. Okay, and you saw the first time I ran it, it actually crashed. This time, it's hung. Now I can hit pause to see where is it. So I hit pause, and I can go look at the call stack. So let's go to the debug tools again. And this is the one, it paused, basically this is the one that got the pause, but then it stopped all the threads. So I can go look at, well, where are you? Okay, it's in my wave algorithm. This one's still starting up. This one's still starting up. This one's still starting up. So this one is, let's see, where was that one? Okay, this one is in the priority queue. Return if it's empty. Okay, so I can, when I have multiple things banging in the priority queue, I can actually get it in states where it kind of, you just get into chaotic behavior. Like you get a hang where it's checking is it empty, and it seems to be partly empty and then not empty, and you just get stuck in an infinite loop. So that's what's happened this time. I can basically say continue, but I appear to be in an infinite loop. So anyway, any of these kind of behaviors, you go, looks like a parallel race condition, turn off parallelism, make sure it goes away, start using the debugger like this. And you have to really reason about your variables. It's actually fundamentally a bit harder now to find things in the debugger. Okay, so I will stop running this. Let's see, I think I've got a couple more things in the slides if you guys have time. Okay, so we were creating this matrix. That was what we originally set out to do. Let's just talk about storing it. So I might actually store this in a vector of vectors, and I might store not just the times, but actually the travel path. So let's say I've got some data structure called path that I've defined. It's got the path, maybe I store the travel time in it too. And I've basically shown you the code to do this, but I've changed it a little bit on this slide. I basically am using pushback. So let's see what I'm trying to do. So I can store a matrix as nested vectors. You saw this in milestone 1. So the first vector could be like the index of our source. The second vector we could access by the index of our destination. And then every entry is a data structure called a path that has like a travel time and maybe all the street segments. So this first row is like all the entries in my matrix where the source intersection is like index 0, right? It's like our first interesting intersection. And this entry would be the paths for source, the intersection whose index is 1 to the intersection whose index is 2, okay, from our interesting intersections vector. Okay, so I've written this code to load this up. And I guess focus in on this. Like you've already seen all this, find paths and so on. Just in this for loop, is this code okay? And the find paths is okay. We just talked about that. I'm not using global variables and stuff. Let's just assume that's fine. Is this okay? I'm basically storing it in the matrix by saying paths.pushback. Paths is the name of my matrix. So I'm just basically getting back a vector, right? My find paths returns a whole vector of these paths. And that's fine. That's what that multi-destination Dijkstra can do. And then I'm basically saying add that to my matrix. New row, put it in the matrix with pushback. And just go through every row, right? For every row corresponds to a different source. So let's just go through all the rows and just add them in one after another. So in serial code, this is fine. Okay, this would work. In parallel code, will this work? Is a strong hint, probably not. Why am I showing it to you? So it won't work. Why will this not work in parallel? Well, it worked in serial. Any ideas? What's that? Yeah, the ordering of pushback is not, it's kind of like my, it's a lot like that case where I was printing to the screen. Like what order are the rows coming back? When I did this serially, I know row 0 was first, then row 1, which is important because later I'm going to index them, assuming, row 0, row 1, etc. These are going to come back in some unknown order, right? I might get row 13 first, and I'll put that in as row 0. Makes no sense, right? The rest of the program can't deal with that. So that's my first problem, right? The order is arbitrary. Second problem, which is more subtle maybe, is the way I'm doing this, the first dimension of my vector I haven't built, right? I'm just saying do pushbacks. And remember way back in the second tutorial, we showed that pushback actually can reallocate the internals of the vector. We doesn't have enough internal storage, it basically makes more storage, copies everything over. When you have multiple threads, one thread can trigger that reallocation, the data is being copied over, and another thread comes in and tries to store something. That'll produce chaos. Very hard to say what'll happen. It might crash, it might hang, who knows? Okay, so there's two problems in this. So the solution to it is we basically need to make that first vector in advance. If we make it in advance, we know it won't be reallocated, and we're not going to use pushback. We're going to basically get a row back, we're going to store it in the right spot. With this new code, it's not really any more complicated, but basically we always store something in the right row, and there's no chance that we have like a reallocation where the vector gets bigger and copied as our threads are running. So there's some subtle things you have to think about, right? Because if you just thought about that pushback, it looks perfectly fine serially, but it's wrong parallel in actually two different ways. Does that make sense? Okay. Okay, so I already talked about this, right? So if you want to debug parallel programs, try disabling it to make sure it goes away. You can use the debugger, and then try to privatize variables first. If you have to, you can use OpenMP critical once you find the race condition. I talked about this in lecture. You have Amdahl's law is a famous law that says how much faster can you get with parallelism. You can derive it pretty easily. But what it basically says, let's say I took a program where half the work is serial and half I could make parallel. No matter how many processors I throw at that, I'll never get the whole program to run more than twice as fast. So I have to take that into consideration when I decide, is this worth doing? If I have a program where only 5% of the work is serial, well then with a lot of processors I could make it 20 times faster. But even if I had, like, in this case, 65,000 processors, it's never going to be more than 20 times faster. So it's basically a very useful rule to keep in mind of, is it worth my time to speed up this? How much effort should I do? Unless it's a big part of your program, it's generally not worthwhile. We kind of talked about this as well already, so that's just a summary. Okay, final M4 suggestions. Make sure you get something simple working first, because agile development. You're going to run out of time on M4, so if you run out of time, you got a pretty good answer. You're happy. If you run out of time, you have nothing working, you're sad. That's a high-stress way to live your life. So you can use a simple travel time estimate, like don't even have to do pathfinding at first. You can use a simple ordering solution. Greedy works pretty well. Get that going first. Make sure you can return a legal solution and pass all our test cases, and then you can try all sorts of stuff. Try better cost estimates with pathfinding. You can try parallelizing, you can try perturbation algorithms, etc. But try those things after you have something working. And you can try, the way you can divide tasks amongst team members here is different people can be trying different improvements. Many of them won't work out, but they're actually still useful to write down what happened, like what is the QOR, because it's very interesting for your OP2, right? Some of the most interesting OP2s aren't just, this is what I did for my final algorithm. It's like, I tried these things, and interestingly, this works quite well, this works a little, this doesn't work at all. Having numbers for that, so you keep the numbers as you're doing it, makes that presentation a lot more interesting. So don't just focus on the final answer. Keep some of your sort of record of what you're doing. Okay, and that is it for tutorials. Thank you.